In this video, we're going to look at methods for solving second-order linear constant coefficient differential equations. These are equations of a very specific form, namely the form is given in this first box. This is probably one of the easiest topics in the course. For one thing, we don't have to deal with integration here, which has been one of the challenges for some of us earlier in the course, and perhaps will be later on in the course, especially when we deal with Laplace transforms. So we don't really have to do much with integration here. Fortunately, this type of equation is one that comes up a lot in applications. So here we go. A little bit of theory, first of all. Based on the discussion in the previous section, we are always looking for a general solution of that equation of the form given in equation 2, c1y1 plus c2y2, where y1 and y2 are two linearly independent solutions of 1. Based on our previous experience working with differential equations, we're going to try and see if we can find exponential solutions, something of the form e to the lambda x, where lambda at this point is an unknown parameter, and we're going to use the differential equation to determine possible values of that parameter. If we take that inspired guess and take the first derivative using the chain rule, we get lambda e to the lambda x, and the second derivative similarly would be lambda squared e to the lambda x. Next, we take those expressions for the function and the first and second derivative and plug those into our original differential equation, and we get this equation, this equation for lambda, which looks kind of nasty, but notice every term contains the common factor of e to the lambda x. E to the lambda x is never 0, so we just divide that out, and we're just left with this quadratic equation at the bottom. So with this method for this type of DE, everything comes down to just investigating the roots of that quadratic equation called the characteristic equation for the differential equation. Here's a simple illustration of the method. This is actually a differential equation which we looked at a little bit in the previous section, so we already know based on the discussion in the previous section what the solution should look like. Based on the approach outlined on the previous slide, the characteristic equation would be lambda squared minus 25 equals 0, which we can easily factor, and we get lambda minus 5, lambda plus 5 as the linear factors of that quadratic on the left-hand side. So that gives us lambda 1 equals 5 for one of our roots, which gives us one solution. Y1 is e to the 5x. And then our other root is lambda 2 is negative 5, gives us our other second linearly independent solution. Y2 is e to the minus 5x. So that gives us our general solution in agreement with the discussion in the previous section. That gives us our general solution, c1 e to the 5x plus c2 e to the minus 5x. So there's a very simple basic example of the method. Now there are some complications, however, with the method which we're going to need to discuss to be able to use this method on any equation of this type. So here's a quick summary. There's our differential equation. Any second order linear constant coefficient homogeneous differential equation has that form, or can be put in that form. We use our inspired guess and come up with the characteristic polynomial. And the characteristic polynomial in our first example factored. You may or may not have a polynomial that can easily be factored. Whether it does or doesn't factor, you can always use the quadratic formula if you need it to find the roots of your characteristic polynomial. And once you do that, your solution is based on the nature of those roots. The simplest case is the case that we've already encountered in example 1, where the discriminant, b squared minus 4ac, the thing under the radical in the quadratic formula, is positive. In that situation, you have two real roots to the characteristic equation, like we did in example 1, two real roots. And when you have two distinct real roots, then you can just write your solution down. That's the simplest possible thing that can happen in connection with this method. Now, there are some complications, however, that you're going to run into sometimes with this method. So, case 2 is a situation where the discriminant, the thing under the radical, is 0. In that case, you have exactly one real root. So that's only giving you one solution. But we know from the theory in the previous section that we're looking for a general solution that has two different linearly independent solutions. It turns out your second linearly independent solution is just x times that exponential. There's a little bit of theory discussed in the text and some additional theory outlined in the homework problems that will help you get a feeling for why your second linearly independent solution should have that form. The other thing that can happen with this method is you can have a situation where the discriminant, the thing under the radical, is less than 0. In that case, you would have no real roots, but you would have two complex roots, which would be complex conjugates. By the way, we are assuming for all of this that our coefficients in our original differential equation are all real numbers. So if that's the case, then if the discriminant is the thing under the radical is less than 0, you're not going to have any real roots, but you'll have two roots which will be complex conjugates, numbers of the form alpha plus or minus I beta, alpha being the real part of the complex number and beta the imaginary part of the complex number. This is a very interesting situation that has a lot of connections with Euler's formula, which we'll discuss a little later in a later video. There's a little bit of a discussion in the text in more detail about what happens here, but the least you need to know is in that situation, your general solution turns out to have that form. There are some other ways that people sometimes write the general solution in this case, especially sometimes some engineering and physics folks. There may be a preference for putting the solution in complex form in this situation. Again, there's a lot more details in the text about this, but most of the time for us, we will go ahead and put our solution in real form, which is what I've done here.